Hello and welcome to another video. In this video we're going to be going over maximal rectangle, and in the problem you're given a matrix filled with zeros and ones and you want to find the largest rectangle containing only ones and return its area. And the dimensions are pretty important here, so the dimensions are 200 by 200, or that's the most it can be. So essentially you can have something like the worst case, you can have like an n cubed log n or something solution, and that would work. Anything worse than that would fail, like kind of the fourth or something would fail. So there's kind of like two ways to do this. One's a little bit more intuitive and one's pretty hard, and we'll talk about the intuitive one pretty quickly, and then we'll talk about the hard one. That is also a solution to another problem. So the intuitive way is basically, for most of these problems, when you're trying to get these rectangles, you usually want to say like, okay, let's say this cell is the bottom right of my rectangle. How many possible rectangles can I make here, and like what's the least amount of work I can do? Well, let's actually look at this example. So for this cell, so if this cell is the bottom right of a rectangle, what are like the best rectangles to make? So if I just only include this row, then this is going to be a rectangle. If I include 2 rows, then this is going to be a rectangle. And if I include 3 rows, then there's nothing because this is a 0. But how do I do that pretty efficiently? And so the way to do it pretty efficiently is reasonably straightforward. We can just count up like sequences of ones that we have, and then like add them up. So for example, here we have like 1 0 1 0 0, so there's nothing here. But here we're going to count them up left to right. So this is like 1. Now we have 2 1s, so this is going to be a 2. And this is going to be a 3. Then we have 1 2 3 4 5, and then the rest is going to be the same. So for this cell now, we know that, like, okay, if this is the bottom right of a rectangle, if we just use this row, then the number of ones we have here is 5, because we're just counting up how long this is. And anytime there's a 0, we can like reset this count. Then if we use 2 rows, well, this has 3 ones and this has 5 ones. So if I use 2 rows, it's going to be the minimum of these two things. And if I use 3 rows, it's going to be the minimum, and so on and so on. So as soon as you get to a 0, you can stop. But essentially, you can just go up the column, and the width will be min of all items in column that you're on, right? And then the height will be like the bottom, or the top minus bottom of the column. So for example, if as I'm going up, like the first thing I'll consider is this will be height 1, now this will be height 2, now this will be height 3, and so on and so on and so on. And that would basically give you an n by m by, so for every single item, you're going up the column every single time. So this will give you another m. So it'll be like n times m squared, which would pass. But that's basically what you do. And then if you have a bunch of numbers, like let's say we're going up a column and it has a bunch of numbers. Let's say numbers is like 1, 2, 3, 4, 5, for example. And we're considering, okay, for this 5, what's like the biggest rectangle we can make? Well, the rectangles we can make is if it's one column, or let's make these a little different, I guess. So let's say it's like 6. Well, let's see here. Let's give it a 6 here. So something like this. Okay. So if we're on the bottom row, then it's going to be a 1 height times 5 width. If we're on 2 rows, it's going to be the minimum of these two. So 4, or it's going to be 2 height times 4 width, and then 3 height times 3 width, and then 4 height times 2 width, and then finally 5 height times the minimum of these, so 2 width. And then you basically get all of these areas, and then just the smallest one, you just keep getting these, and then the smallest one is going to be your answer. Or, sorry, the biggest. So you do that for every single column. So first you pre-compute this like sequence of ones, then you do this thing, and it's pretty straightforward. Now there's another way to do this in n by m time, and it's a lot trickier. So let's go back actually to this, and it's also going to be easier. So we counted up the stuff for columns. So instead of that, we can actually count it up this way. So we're going to do the same thing, but we're going to count down because it's easier to look at. But you could still do this column approach and do the exact same thing. You just have to switch some variables. And actually, I think the best solution would you would actually have I think anyway, the best solution. So this is going to be the solution I'm going to show you is going to be O of m space, I believe. where m is the number of columns. But if you wanted like the optimal, you could actually figure out what is smaller rows and columns and do it that way. But I'm just going to show it this way, and then you could do it the other way if you want. It's basically the same thing. So we're going to do the same thing. We're going to count these up. So it'll be like 1, 2, 3, 4. And then 1, 2, 3, 0, and then 1, 2, 3. So we're basically doing the exact same thing as we did before. We just count up like a sequence. Every time there's multiple ones, we just add it up. So now what we're going to do is for every row, we're actually going to say, like, what's the best rectangle you can make on the row? So, for example, for this row, the best rectangle you can make is area 1. Now, what about here? So this row includes everything up until this row, right? So it's going to include this whole thing. Because this 2 means this rectangle is of height 2, like this. This rectangle is of height 2, and so on. So here, the best thing you can make is a 2 by 1 rectangle, right? Or actually, no, the best thing you can make is a 3. Yeah, it's a 3 width and 1 height. Then here, you'd have to figure out and so on. But essentially, your problem comes down to, for every row, let's get these numbers, and let's figure out what's the best area I can make. And if I can do that in linear time, then I have an n by m solution. So what we're going to spend our time focusing on is, given a row of these numbers, where the number represents the height of the rectangle, right? So it's a whatever this height is by 1 rectangle, what's the biggest rectangle I can build across this whole thing? And so that's where this comes in. So let's say we're given, so this would be like the same thing as being given a row of 2, 1, 5, 6, 2, 3. And this is actually another problem called largest rectangle in histogram. So essentially, you're given this, it just means this drawing here. So the first item has height 2, the second item has height 1, third item has height 5, and so on, so on. So you're basically asked, like, what's the biggest thing I can build with this? And your answer should be this rectangle over here, which is a area 10 rectangle. But how do we figure that out? And so the way to do this, the efficient way to do this, is basically, instead of figuring out, like, what are all the rectangles you can build, we just have to figure out, like, given, like let's say we want to use a cell. Like, let's say we have to use this cell, right? Like this thing in a rectangle. Well, what's the biggest rectangle we can build with this, right? Well, if we have to use it, then we can go left and right, as long as the area to the left and to the right is at least this high, right? Because let's say this whole thing was empty, right? If this whole thing was empty, then we couldn't make a rectangle here, because like we try to stretch it out to the right, but we can't because there's nothing here. So essentially, for example, for this, the biggest rectangle you can make using this would be, it's kind of hard to see like this, so I'm just going to draw it. So it'd be like this. Let's see here. Let's use this. Be like this one over here, right? Because you can't make it any higher, because if you made it any higher, there's nothing here. But if any one of these cells was just completely empty, then you would just stop there. And for example, if I said, okay, what if I want to use this cell? What's the biggest rectangle I can make? Well, it's actually only going to be this one, because you can't go left or right because there's nothing here, right? In order to go left or right, these rectangles have to be at least this high, and they're not. So that's kind of the idea, is for every cell, we're going to figure out, like, what's the biggest rectangle we can make using that cell? Like, what's the width of the biggest rectangle we can make? And then the height is just going to be the height of the current cell. So essentially, like, let's say we have to use this cell, we're just going to go left as much as we can. So left, we can't go here, but we can go right up to this. So the biggest rectangle we can make using this cell over here is this one over here, and so on and so on and so on. But how to use this efficiently? Well, if you think about it, basically for a rectangle, as soon as you hit a rectangle that is smaller than our last stored rectangle, like let's say we have this stored, right? But we hit a rectangle like this. So because we hit a rectangle that's smaller than a last stored rectangle, the right bound for this rectangle is now this rectangle that we hit. So that's how we get the right bound, right? We have rectangle stored, and then the next rectangle we hit will be the right bound for it. But what's the left bound? So the left bound is actually going to be similar. We can just store rectangles in increasing order. And then that way, if we store rectangles, like let's say we store rectangles in like 1, 2, 3, 4 or something. And then so this is our stored rectangle, and then we hit like a 2. So if this rectangle has height 4, this rectangle's left bound is actually the one right below it, because this rectangle can't go left to this one because this one's too small. And its right bound is going to be the next rectangle that we hit that's right below it. So essentially we're going to have a... and this is pretty confusing because this is literally like another hard problem. So if you want to just stop at the first solution I showed you, like that one's a lot more intuitive. But essentially we're going to have a monotonic increasing stack. But you will have numbers that are equal to each other because let's say this whole thing had area 4, like those would all be valid, right? Like if this was like 4, 4, 4, 4, 4, 4, 4, you could use all of these to make one rectangle. So the stack will be increasing or equal, but it will never be decreasing. And so let's walk through that with this and kind of show exactly what I mean. So we're going to have a stack here, and we're going to go through our items. So we're going to go to this first item, and we're going to say, okay, well, there's nothing in our stack, so let's just put... And the other thing is we can just put the index of the item in the stack because we'll have an array. Like this format won't actually look like this. It'll just be an array of heights. So this stack will have nothing, so we're just going to put in this index 0. And this index 0 will have a height of 2. Then we get to a height of 1. So height of 1 is less than height of 2. That means the right bound for this is actually over here, right? And what's the left bound for this? Well, so actually, if we get to this value, we can just pop our index 0, and its right bound will be 1, index 1, and its left, because the stack is empty, that means its left will just be the start of this thing. So the width of the rectangle we can make is just going to be I. It'll just be 1, right? So because the left is basically 0. Because there's nothing to the left. So the width of this is 1, and the area we can build is 2. So we'll just store that somewhere. We'll store like area is equal to 2. And now we don't have a stack anymore, and we are going to put in this 1. So now we can keep going. You can calculate the right and left in many different ways, but essentially you need to have some kind of calculation to figure it out. And if the stack is empty, basically the width of your thing is just in the index you're currently at. Okay, so we have a 1, so that's fine. Now let's go to our next item. So our next item is actually bigger than our 1. That means we're just going to want to put this on our stack. So we'll put on this index 2. Then our next item is bigger than our last item on the stack, so we'll put that on as well. Now 4 is smaller than, like this item at index 4 is smaller than both of these. So we need to be popping these items off. So we're going to pop off 3. We're going to pop off index 3. And index 3 has a height of 6. And remember, its right bound is the thing we're putting on here. So its right bound is just 4. But what's its left bound? So its left bound is the item right before it on the stack, which was this index 2. So this is just going to be 2. And so what's the actual, like what's the rectangle you can make though using this? It's actually going to be this rectangle here, right? Actually, no. It's not going to be that rectangle. So its left bound is 2, meaning I can't include this value and I can't include this value. So the rectangle we can make is actually between these two. So it's going to be this one over here. So it's just going to be right minus left minus 1. And so the width of this rectangle will be 1, and its height will be 6. So we have a rectangle of area 6. So now this is better, so we'll just update this. Okay. So now we can pop off more stuff though, because the item we're trying to put on is this, but we still have this index over here, right? This index 2. So this index 2 is still bigger than this index 4. So we're going to pop off index 2. So pop off index 2, and its value is 5. And what's its left? Well, its left is the item that's right before it on the stack, right? This item over here. And that's correct, right? Like, if we want to stretch this out, the farthest we can stretch it is between these two indices, right? So we can stretch it like this. That will be this rectangle. So its left will be 1, and its right will be 4. And so the width is just going to be right minus left minus 1 again. So that'll be 2. So our width will be 2, our height will be 5, so we get an area of 10. So now we improve to better than this. So we get an area of 10, and then we keep going. So we can get rid of all this. And now our stack is just this item here, this index 1. But now index 1 is less than 4, so now we can push the 4 onto our stack. Then we can also push the 5 onto our stack because that still keeps it increasing. Now that we did that, we still have to pop these 3 locations off the stack. But notice that because these values are on the stack, now these values don't have a right bound. So for index 1, we can actually make a rectangle going all the way to the right. And that's correct, right? Then for index 4, we can make a rectangle going all the way to the right. And for index 5, we can make a rectangle going all the way to the right. So now we have to pop these items, and we have to figure out their left bound. So we pop off the 5, so that index 5, its height is 3, and its right bound is just completely out of bounds, but what's its left? So its left is index 4. So that means that so the length of this whole thing is 6, and this thing's left is index 4, so it's going to be 6 minus 4 minus 1 is going to be like the width of this whole thing, which is just 1. So we do 1 times 3, which is less than our thing, so we don't care about that one. Then we pop off the 4. So for 4, its value is 2. And then what's its left and right bound? So its right bound is 6, because remember it can go all the way. So its right bound is 6. Its left is the last thing on the stack, which is 1, because it can go all the way up to this thing, right? Like these are the 2 places it can go. It can go like all the way up to this. That'll be this rectangle here. And so this is just 6 minus 1 plus 1, I believe, or minus 1. So this is just 4. So 2 times 4 is 8, and that's correct because that's this rectangle, right? This rectangle is area 8, which is smaller than our total, so we don't care about that one. Finally, we pop off our 1. And so for our 1, we have no stack, and we have no, like, so that means if we have no stack, that means the left bound is over here, and the right bound is over here. So that's just length 6. So this is length 6 times 1, which is area 6. So for this problem, our best thing was 10. And basically, we just apply, we can make this function, and we can just apply this function to every single row. So we'll call the function with this row, we'll call the function with this row, with this row, with this row, and then our best result out of all of those will give us our area. So it's definitely kind of tough, and I do think the first one's a lot easier with the columns, where you just check for, if I use this column, like, what is it with length 1, length 2, length 3, like that one's a lot easier. But that one is, roughly n by m squared, and this one will be n by m, and it will also be only m space. And like I said, you can technically make this thing, you can like rotate it, right? So you can do it like this. You can still make these rectangles and then just like change your inputs if you want to, and that would make it, instead of m space, you can make it like min and m space if you want to. But that's already like going kind of far, so let's get into the code. The code's kind of long as well. Okay, so we're gonna have rows and columns. So that'll just be matrix length, and columns will be matrix 0 length. And we also are going to have this interarray totals, which will be, so the interarray totals will just be the total for the row, which will just be recomputing at every single stage, right? So here the totals will be like 1, 0, 1, 0, 0. Here we can just update and so on. And to update one row to the next row, you just take your previous total, you check, is there a 1 here? If there's a 1, you add 1. If there's a 0, you just reset to 0. So totals will just be new interarray, that will be length columns. And our area will be 0. Then we can loop. We can just have a nested loop. So for int row equals 0, rows less than rows, and column as well. So basically, like I said, if the current cell is a 1, then we increase our old one by 1, and if it's a 0, we just reset. So if matrix row column equals 1, we increase. Otherwise, we reset. And then we just pass, like after we're done filling out this whole row, we just pass that into our function. So we're going to make a function that I'll make below this one, and that'll be area equals the maximum of the old area and rectangle area totals. And then we can just write this function, and then finally we can return area down here. And so we can write our function right over here. So we can make a function, which is just what I was describing. So rectangle area, and it will take an interarray of rectangle heights. And so what we can use is we can actually use a stack, because in Java it's pretty useful actually, because you can look at the last element without doing like the length minus one thing. You can use a stack or a simple array, either one's fine. So I'm going to use a stack. And we're going to have a max area. And so this is going to be the same thing I was talking about. So we just go through all of our heights. So if our int equals 0 is less than heights length. So basically, as long as our stack is non-empty and the top item on our stack is bigger than the current item we're putting on, then we're going to pop, right? Like our picture. So if we're putting on like this, let's say, this item, then we're going to need to push off these two. So that's what we're going to be doing here. So we'll say while stack is not empty and heights I is less than heights. And remember, the items we're going to store on the stack are just indices. You could store a tuple if you want of like the index and the number, but because you can just access it, I'm just going to store an index. So you can actually use a peak to get like the topmost item. And then we're going to get like our topmost item. So we can say int top equals stack pop. And we're going to calculate our width of our actual item. So width. So if the stack is empty, that means the width is just I, right? Because like, let's say we're trying to push on this item and that causes us to pop off this item. If there's nothing below this, that means this thing can go all the way left. And if this thing can go all the way left, that means it can go all the way left and it goes all the way right up until this item. So it's kind of messy, but basically that would mean that if we pop off here, the width of our last item is just going to be all the way up to here, which would just be I, right? So 1, 2, 3, 4. So we can check for that. So we can say stack is empty. And so if it is, then it will just be I. Otherwise, it's going to be I minus. So remember, the two locations will be like, let's say we have this item that we popped. It's going to be the right bound will be here, the left bound will be here, and then the total area is right minus left minus 1. So we can say I minus stack peak to get the last item minus 1. And our area, our max area, equals, I guess this will be more like height, not top maybe. So height. Actually, no, this will be this won't be the height. This will be like the index. So this will be like J or something. So I guess maybe like if you want the height, you can do this. You can say heights stack pop. That's more accurate. And then the max area is just going to be max of the old area and width times height. Okay, now that we popped off everything, now we just push our item onto the stack. So stack push this current index. Then when we're done with the loop, we might still have items on the stack. So remember, like we might still have items. It'll just be an increasing stack in the end. So like in this case, we'll have this item, and this item. Then we have to pop off one at a time. So we can say while stack is not empty, we will pop off the item. So we can do the height thing again. So height equals heights stack pop. And the width will depend on, so the width, remember, like I said, at the end of your stack, the right bound will always be out here because there will be nothing bigger, because like we'll have items like 1, 3, 5, 7, and so on. So when we pop the 7, there will be nothing bigger or nothing smaller than the 7, right? Because if there was something smaller than the 7, we would have popped off the 7. And the left bound will just be the item that's left, or if there is no stack, that means, like, let's say we pop off this item. If the stack is empty, that means it's this whole thing, which is just the length of the array. So we can say int width equals, we check for the empty stack again. Only now, if it is empty, then the width will just be the whole thing. So heights length. Otherwise, it's going to be heights length will be the right bound. The left bound will be stack peak and -1. And our max area is going to be the same thing. So now we just return max area. So definitely a long one and a lot to do, and it's kind of hard to explain all these because it's basically 2 hard problems in one. But so let's see what we did wrong. Oh, cool. Oh, okay. Matrix. Let's take a look at what we actually did wrong. Cannot find symbol. Yeah. Okay. Okay, so definitely this one's a lot tougher because it's basically the largest rectangle in histogram and this in the same problem, which is kind of tough. You can go with the easier solution. It's a lot less code, and it's just going to be a little bit slower. But for this one, this is going to be time. So this is n by m, or m by n or something, because essentially we copy our matrix. Then for every row, we build the row, and then we walk through the row, right? So to build the row takes to build the row, we basically go through a column, and then to walk through it again to get the stack is going through the column again. So essentially, we just go through the column like 2 times, and then we do that for each row, so it's rows times columns. So this is n by m and space. In our case, we store the heights of each column. So this will be so if this is like n by m, or let's call this like row times column, maybe rows times columns. This will be columns. But like I said, if you wanted to like have like the best performant function I could think of off the top of my head, you would figure out which is smaller rows and columns, and you would basically do this inversely to, instead of storing, like, let's say columns is actually smaller, then you would do this thing, right, where you rotate it around and you do the histogram this way and it would still work, right? You rotate it this way and you store like this. It's harder to look at, and you'd have to figure out exactly what you store, but it's basically you literally just inverse. I think everywhere it says row, you just switch the column, and theoretically I think that would work. You'd have to like double check everything, but roughly that. But yeah, it's gonna be all for this one, kind of a long one, so hopefully you liked it. If you did, please like the video and subscribe to the channel, and I will see you in the next one. Thanks for watching.